All right, so just a couple of things that I want to point out. Remember that our homework is due on Monday, even though Monday is a holiday. And of course, since Monday is a holiday, don't come to class. The other thing that I wanted to mention is that I am currently trying to get you guys access again to the study guide to the book. And it was my understanding from the beginning that because you were given access last semester, you'll get it this time too, but I didn't know what the mechanism for that was, and so I thought I got it set up yesterday, but then they gave me the wrong number to link it to the, I don't know. So the publisher's end is working on it right now, so hopefully very soon we'll have access to that. All right? There's an SI tonight. Okay, so go if you got a chance. All right, so we are talking about NMR spectroscopy. We've talked a little bit about how we get the signals, and so the theory, and what information we get. So far, all we've really done, though, is talk about if we look at a given structure, how many signals should we observe from that. All right, so today what we're going to do is we are going to go on and talk about chemical shift. So that's the position along the x-axis of the graph. And integration. This tells us the relative number of protons represented by each signal. All right, and if we get any farther than that, splitting is the next thing. All right, so I already gave you, and we don't have to worry about this for calculation, but just for discussion here, that the relationship between the frequency, okay, of where we would see the peak, or the frequency corresponding to the energy gap, this would equal a constant called gamma B over 2 pi. And remember that this B value is the external magnetic field. Okay, so this is the magnetic field generated by this big superconducting magnet. So if we look at this equation, though, it suggests that all of the protons would have the same frequency. All right? And what good would this technique be if every proton in the spectrum was all at the same frequency at the same spot? Okay? So let's look. Luckily, that's not true. Okay? So the way that this kind of in general works is that we have the external magnetic field. We have the nucleus that we're looking at, the proton, and the electrons that are around the nuclei create their own magnetic field. And I think because we're looking at nuclei on one side, and those are positively charged, we have electrons that are negatively charged, so this magnetic field from the electrons, which we could refer to as B local, so this is the local magnetic field, aligns in the opposite direction to the applied magnetic field. So if we draw this out down here, we could draw this big arrow for B0. So this is the applied magnetic field. The B local is the local magnetic field generated by the electrons around each of the atoms. And so let's just say, for example, we have this, and it's aligned in the opposite direction. So this is B local. Okay, so the magnetic field that is felt or experienced by the nucleus is the difference between these two. So this B local effectively blocks or shields the nucleus from the full extent of the applied magnetic field. Okay? So we would have some smaller amount here. We could call this B effective. Okay, and this is what the nucleus would actually experience, and so this is the magnetic field that would control the frequency. Okay, so it turns out that the B local value, this one over here, can be influenced by the amount of substitution around an atom, so whether it's primary, secondary, or tertiary, the electronegativity of different groups nearby, and the different pi electron systems that are close by as well. Okay? So because of all of these, essentially each nucleus will experience a different B effective, and therefore they will absorb a different frequency of light. Okay? So this is kind of the general... Yeah? Questions? So let's see how this works. So we're going to look through these different factors that influence this B local. Okay, so here's just kind of another drawing before that. So the electrons create this magnetic field, and here's a diagram. So here is this B local here. It's kind of similar to the drawing that I did. And so, in fact, that cancels out this part of the applied magnetic field, and the nucleus only feels this much. Okay, so this would be this B effective. So because it's experiencing less magnetic field, if we started here and the frequency increases going this way, this shielding would cause the signal to move to the right. Okay, and we call this upfield. All right, this would be the act of shielding. Okay, when it moves to the right, it's being shielded. Okay, if this local magnetic field was much smaller, like it is here, then the nucleus would feel this larger B effective, and the signal would absorb a higher frequency light, because the larger the magnetic field, the bigger the energy gap, the higher the frequency of the light that's absorbed. So this would be called deshielding. Okay, over here, this is going to be essentially protons that are in electron-rich environments, because the more electron density there is, the bigger the B local is. Okay, and this one over here would be in an electron poor environment, so there would be very little shielding. Okay, so this is the general trend. So let's... Pretty soon we'll get to that slide. Okay, before we give any values or anything for chemical shift, let's look at the scale that we usually use. Because what I've said is that the frequency depends upon the magnetic field, right? And so, based only on that, if we went downstairs in this department and ran an NMR spectrum on our 300 megahertz NMR, we would get different chemical shifts than if we ran the same sample on the 500 megahertz NMR, because they have different magnetic field strengths. So what we do is we just basically normalize the scale, okay, and we compare the frequency in hertz to a standard, okay, and the standard is this one right here. This is called tetramethylsilane, or referred to as TMS. And this is defined as having a chemical shift of 0.0, we do it in parts per million. Okay? So when we calculate a chemical shift. We use this, what's called the delta scale. And what we do is we take the distance between TMS, the standard, and whatever signal we're observing. Okay, this is a distance in hertz. So for example, here's our spectrum. Here's a peak right here. Turns out, so here's 0, and this, we could have a peak for TMS right here. Okay? And let's say that we're running this experiment on a, what should we do first here? A 300 megahertz NMR. Okay? And let's imagine that this chemical shift here is at 900 hertz. Okay? So what we would do to get the delta scale is we would take 900 hertz divided by 300 megahertz, and this ends up being 3.0 parts per million. Okay, because it's hertz per megahertz. If we ran this same sample at, let's say, 500 megahertz, then this signal right here would be at 1500 hertz. And so we would have 1500 hertz divided by 500 megahertz. This still equals 3 parts per million. All right, so for a given field strength, what happens is we essentially have something like this. So here, let's put up here, this is in parts per million. This would be 1.0, this would be 2.0, 3.0 on up. If we looked at the scale in hertz, this would be 300 hertz, 600, 900. Okay, so we, in a 300 megahertz NMR, we have 300 hertz per every part per million. If we have this in a 500 megahertz NMR, then this would be 500, this would be 1,000 and 1,500. So in a 500 megahertz NMR, we have 500 hertz in every part per million. Okay? So we've kind of normalized this, so no matter what instrument you use and what magnetic field strength you have, this part per million, this delta scale, we come up with the same value. Yeah, question?
Are there any advantages to changing the operating frequency of the spectrometer?
So the question is, are there any advantages to doing different magnetic field strengths, right? Definitely there are. So for one thing is that the higher the magnetic field, the stronger the signal. Because what we really are observing in the NMR in a more complicated sense is there's always a slight excess of spins in the more stable spin, the plus 1/2 versus the minus 1/2. And as the energy gap gets bigger, that population excess gets bigger as well. Okay? And the more there are, the more excess spins there are in the lower energy, the stronger the signal is that we observe. Okay? The second thing is the peaks that we look at will be more well dispersed at the higher magnetic field. So yeah, it's worth, depending on the types of samples and molecules you're analyzing, to spending the extra big bucks to getting the big magnet. Shifts go. So here's the same spectrum we saw before. So these are kind of things we'd already mentioned. Protons on this right side are in electron-dense environments or electron-rich. On the other end is more electron-poor. Okay, the electron-rich causes more shielding. Okay, so these are shielded protons, deshielded. The right end of the scale we called upfield. Left side is called downfield. And that kind of comes from an old instruments that we don't really do it the same way, but the language has stayed the same. Okay, to the right are the lower frequencies. Left is the higher frequencies, right? Small delta values, large delta values over here. So this delta scale usually goes between about 0 and maybe 14 parts per million. Okay, that's the range that we cover. Okay? So the first thing that we can look at is the effects of substitution on the chemical shift. So these are just alkyl groups here. We're just looking at the protons that are shown. And essentially the trend here is if we start with just a methyl group here, this is a primary position. We have a rather low chemical shift at parts per million. If we go to secondary, it goes up a little bit. Tertiary goes higher. Okay, so the more substitution, we see small shifts to a higher frequency. Okay, they go downfield. All right, that's the first trend, too. The next thing is the presence of electronegative groups. All right, so if we start with a methyl group like this, usually if it's on the end of a chain, it's about 0.8 parts per million. If we add a group to it that's more electronegative, like if we just add on this methyl group, we add a nitrogen. Nitrogen is more electronegative than carbon is, right? And so that's going to pull electron density away from the methyl group, creating a delta plus around that methyl group. This is the act of deshielding. It's pulling electron density away from it. And so we see a downfield shift. So it goes from 0.8 to 2.4. If we, instead of nitrogen, we put an oxygen on there, oxygen is more electronegative than nitrogen is, then we see even more deshielding, right? We build a stronger delta minus there, or delta plus, that's right. Follow my hand and not my brain. And it shifts to 3.2 parts per million, okay? Up above, we're looking at CH2 groups, and we're looking at a trend down the halogens. We know that fluorine is the most electronegative atom, so it's going to cause the most deshielding. Okay, so the CH2 next to the on the carbon next to the fluorine here is 4.5 parts per million. If it's a chlorine, it's less electronegative, less deshielding, goes to 3.5. Bromine less, 3.4. Iodine even less, 3.2. Okay? So the trend follows the electronegativity there. So if we are thinking about electronegativity, though, let's look at these chemical shifts. So here's a proton on a benzene ring. Here's a proton on a double bond. Benzene chemical shift is 7.3. Chemical shifts for protons on double bonds have a range of 4.5 to 6. So these are very downfield shifts. These are more downfield than any of the shifts we saw, even next to fluorine. So does that really mean that an sp2 hybridized carbon is more electronegative than fluorine? No, it can't, right? And if that was in fact true, then we go to an sp hybridized carbon, then it should shift even further downfield. And that's not what happens. So protons on alkynes are only at about 2.5 parts per million. Okay, so there's something else going on, all right? And this something else has to do with the pi electrons in these systems. So the way that this is often shown, and if we start out with benzene, if we put a benzene molecule in a magnetic field, then the molecule orients and it can cause the electrons to cycle around the benzene ring. So you can see this arrow right here. So the electrons start cycling around here, and it creates these magnetic field lines. Okay, so you've probably seen before pictures of like planet Earth, right, and these magnetic field lines going out of one end and up into the other end. So it's kind of the similar thing. So we have these magnetic field lines, and what we then need to look at is what's going on in the region where the protons lie. Okay? And if we look out by this proton, we see that the magnetic field lines are going in this direction, and that is exactly aligned with the external magnetic field. All right? So in this case, we're going to take whatever this B local is, and we're going to add it. Oops. We're going to add it up here on, up here. So it's going to add to the B0. Instead of shielding, it's going to cause a lot of deshielding, because this, it's kind of messy there, is going to add on because it's aligned with the magnetic field. So the induced magnetic field, or the B local, reinforces the external magnetic field. So that means that those protons are going to feel an even stronger magnetic field. The energy gap is going to get bigger, and it's going to take a higher frequency of radio waves to jump the +1/2 to the -1/2 spins. Okay? So this is going to cause deshielding, and it's going to shift downfield. And so for these kind of benzene rings, the general range is usually like this, between 6.5 and 8 parts per million. It depends upon what's attached to the benzene ring, where that shift will be. Okay? So this is something in addition to just electronegativity. In alkynes, we have similar situations. For alkenes, they show that it orients like horizontally like this in the magnetic field. Here's these magnetic field lines going like this, and again, in the region of the protons, this induced or local magnetic field is also aligned with the external magnetic field. So this is the same story as with the benzene ring. So these protons are going to be further deshielded. They feel a stronger magnetic field, maybe not quite as much as the benzene, and double bond protons are in the range of 4.5 to 6. We essentially have this, we have two pi bonds that are on Earth, are 90 degrees apart, where the orbitals go. And so it creates kind of this cloud of electron density. The electrons can cycle around in this way. And so like the other examples, that creates the magnetic field lines going just like they were before. Now the difference is, though, is the position at where we find the hydrogen relative to the magnetic field lines. Okay, in this case, the hydrogen is up here. The magnetic field lines are then going in the direction opposite of the applied magnetic field. Okay, so these are opposing the applied magnetic field, and so this actually cancels some of B0, causing shielding. So it goes in the opposite directions, and so these are around 2.5 parts per million. Okay, so we have three things. We have substitution, we have electronegative groups, and we have these kind of pi electron ring currents or currents. All right, and if we add, then we can kind of come up with just some general ranges for different types of protons where they will show up in the spectrum. Okay, and like IR, if we just know some general ranges, we can get by doing a lot of the problems. Okay, so let's look at these general ranges. So on the very upfield side, this is all of the hydrogens that are on sp, well, not all of them, but are on just like alkyl groups, okay? So these are just like alkyl down here. Right, and remember, it goes from CH3 to CH2 to CH, right? In that order, we see an increase in chemical shift as we increase the substitution of carbon groups, okay? The next groups up are mostly going to be protons on carbons next to a pi bond, like this one here. All right, and the common ones here are going to be either protons that are on carbons next to carbon-carbon double bonds, so these are called allylic protons. The other common one is protons that are on carbons next to carbonyl groups. Okay, and these run anywhere. The allylic protons are more at the upfield side here from 1.5 to maybe 2 parts per million. Next to a carbonyl, there's more like 2 up to 2.5. And then they have the alkynes in here as well. All right, so 1.5 to 2.5. The next series of groups are the examples that we already saw, where we put some electronegative atom on the carbon that's bearing the proton. And we saw the trends there. It goes more to the left field, to the left side, to the downfield side, the more electronegative that group is. Okay, so oxygen would be more on this side, nitrogen somewhere in here. The halogens would spread over that range. The next ones are protons on double bonds. Then we have protons on benzene rings. And then at kind of the far downfield, there's an aldehyde and a carboxylic acid. Okay, aldehydes are usually in the 9 to 10. Carboxylic acids more like 10 to 12. And carboxylic acids, even like in the IR, that OH is oftentimes kind of broad. Okay, whereas the aldehyde signal would be sharp because it's bound to a carbon. All right, there's a much more extensive tables back in the appendix. And I'll give you, and I'll make this available to you well before our exam and stuff, a table that you'll have on the exam. Okay? But the most important thing are these general ranges. Okay, so before we go on, the integration is the next thing, but let's look at this actual spectrum. Okay, we don't know about the splitting yet, but let's look. There's 3 signals here. If you look on your table for that last one, what do we think would be? Well, let's do the integration first, so I can finish this. So the integration are these kind of curved lines that are going up above the signals, and if we measure from the top to the bottom of this, the measurement, we could measure that thing and just put our ruler down there and measure it. And if we do that for each of these signals, we get a relative number of protons that are under these signals. So these lines are called the integration. So what we're doing is actually measuring the area under the peaks. Okay? We have listed 2 to 3 to 3. But in the molecule, it could actually be 4 to 6 to 6, right? All we get is the relative ratios, all right? Sometimes what we'll get is not just a integration that we have to measure. Sometimes you'll just be given a number, okay? We might just get this number 2 to 3 to 3, or maybe we'd be given a number and we have to divide them out and figure what the ratio is. Okay, but those are always giving the relative proportions of those different protons. All right, so then let's look at this signal. So this one that's most upfield is about just over 1.8, and it's worth 3 protons. Okay, so what kind of a signal do we think that might be? What kind of protons are that far upfield, did we say? Just alkyl kinds of groups, and if this one's worth 3 protons, what do you think it might be? Just a methyl group, right? So that might be a methyl group. All right. We've got this other signal at 2.4, and it's also worth 3. So that's likely another methyl group. But what did we say? What kind of methyl groups might be in that 2.4 range? Well, maybe it's on the edge of that. Nitrogen, or there's another one that we could say that was like 1.5 to 2.5. Yeah, next to a pi bond. So maybe allylic, or in this case, it's going to be a methyl that's next to a carbonyl. Okay, so that's in that range as well. And then at the other end, we have a signal that's at 4.3. It's worth 2 protons. All right, so what we have here is we have a CH3, CH2. This one is so far downfield because it's bonded to oxygen. Then we have our carbonyl, and then we have a CH3 group. Okay, so the CH3 group next to the carbonyl is going to be here. The CH2 next to the oxygen is going to be here. And the methyl group that's just next to another CH2 group is going to be down here. Okay? And it's actually this splitting that's going to tell us that that CH3 and that CH2 go next to each other. Okay, and we'll get to that in just a little bit. Yeah, question?
On, I don't know, a couple slides before, one of the scales says that it's 0.9 parts per million is a methyl, 1.3, 1.9.
Right. So they're kind of ballpark things. So that 1.9 for a methyl group would be if it's just on a long alkyl chain. Okay? So in this case, we don't have an oxygen directly attached, but that oxygen is just one more atom away. So there is going to be some effect through several bonds, but that deshielding is going to drop off the more bonds that it is away. Okay? All right, so integration gives us the relative number of protons under each signal. So it's just measuring an area. Okay, so we've done chemical shifts, we've done integration. The next thing that we want to do is to talk about splitting. Okay, the splitting, so the fact that some of these peaks are more than one, has to do or is caused by what's called spin-spin splitting. And it occurs when non-equivalent protons are on either on the same or on adjacent carbon. So that's an important point. The only protons that split is when they're non-equivalent. They have to have different chemical shifts. Okay? So a signal that's split, it'll be split into n plus 1 peaks, where n is the number of equivalent protons on an adjacent carbon. Okay, so for example, let's draw out our molecule here again. Okay, let's CH3, CH2, here's the oxygen, carbonyl, CH3. Okay, first off, let's look at this methyl group over here. Okay, we looked at its chemical shift already, but notice we said it was this signal here. That one is a tall, just a single peak. And we call this peak a singlet. Okay, and it's a singlet because there are no protons on the adjacent carbon. Right, there's just that carbonyl carbon. All right, if we look at this CH2 right here, That went for this peak over here. This one has 4 peaks in it. This is called a quartet for 4. And it has 4 because we look on the adjacent carbon is a CH3. There's 3 protons. We go N plus 1, 3 plus 1, and we get 4 peaks in the quartet. Okay, so the fact that that's a quartet tells us that there's a CH3 next door. Okay? If we go to the methyl group, this methyl group is way down here. That methyl group has a CH2 next to it. So it has 2 protons, N plus 1, 2 plus 1 is 3, and so this is observed as a triplet. Okay, the triplet, because there's 3 peaks, we know that it has to be next to a CH2 group. Okay, so in fact, this combination of a quartet and a triplet is always going to be an ethyl group. All right, so let's look at where this splitting actually comes. All right, so what we're going to do is look at this simple molecule, and we're going to think about first about this red proton here. Okay, and this is going to be the one that we're going to observe. Okay, so because it's spin 1/2, we know that the adjacent proton can be either aligned or opposed to the magnetic field. All right, so we can have this blue proton can either be aligned, and in that case, what would happen is it would reinforce the applied magnetic field, right? And so part of it would do a downfield shift. The other, but this blue proton could almost equally be in the opposite direction, right? Each proton has 2 possible spins. Remember that the energy gap is so much, we have almost an equal amount in both directions. This one would subtract from the B0, right? And so it would cause shielding. So whereas we start out with this red one, I'm going to draw it like this. We start out with a single peak. That peak is split into 2. Okay, so this was our frequency at the beginning. In one case, this frequency was shifted downfield because we reinforced it, we deshielded it. In the other case, we shielded it and it moved to the upfield side. So because there's 2 possible orientations of the nuclei, we end up with 2 peaks, essentially. Okay? The blue one would be the same, right? Because it has 1 proton next to it. So the blue one would start out with a single peak, and it would be split into 2. And each one, so the red one sees 1 proton next to it, N plus 1, 1 plus 1, we get 2 peaks. Okay, so this would be our, something like this. 2 peaks is called a doublet. Okay, so in the spectrum for a molecule like this, we would see 2 doublets. Okay, and their chemical shifts would be somewhat different because one is bonded next to chlorine and one is next to a bromine. Okay, so we'd see 2 peaks like this. Okay, the distance between the peaks, and we'll talk about this in a minute, this distance would match. Okay, so one peak is splitting the other. We call this a J value. J equals what's called a coupling constant. And for 2 protons that are coupling with each other, they're split by the same J value. Okay, so those 2 match. All right. Okay, so in this case, let's say we're going to observe this proton here. Okay, so here's our proton. Let's just say it's over here. And there's two protons next door. And if this is in energy, we can either have those two blue ones both aligned like this. That would be the lowest energy state if they're aligned to the external magnetic field. We could have one that's up and one that's down. Or we could have the first one down and the second one up. Okay, so there's two possible orientations there. Or we could have, oops, I did that backwards, both of them pointing down. This would be the highest energy. Okay, so we have three possibilities. And notice that these are in a 1 to 2 to 1 ratio. Okay? And so the red peak would end up with 3 peaks, 1 to 2 to 1 ratio. 1 to 2 to 1. This is called a triplet. Okay? It's a triplet. The other way to think about it is the red one has 2 protons next door. N plus 1, 2 plus 1 is 3, and so that has 3 peaks. Okay? So what about the blue protons? What would they look like? It'd be a doublet, right? Because the blue protons only have the proton in red adjacent to it. There's only one signal, that's like the last slide, and so the blue protons would be just a doublet. Okay? And these should be, if I actually drew them right here, in a 1 to 2 ratio, right? Because there's only one of the red and there's 2 under the blue. Okay, so we have both the splitting and the integration. Okay? Everybody kind of following me? Well, what I'm saying here, usually we just draw it up, is the external magnetic field is going in this direction. All right, we have 3 possibilities here. We can align both of these going up. So both of them would reinforce the applied magnetic field, causing this part of the signal to shift downfield. Okay, so that would be like this one here. Right? Then we have 2 in the middle with a spin up and spin down. And those, because they essentially cancel each other, that would be at the same frequency as it started out to be, right? But there's 2 possibilities, so that peak is twice as big. And then the other one has 2 opposed, and so those are both going to subtract from the applied magnetic field, so it's going to cause more shielding, and that one's going to go to a lower field. Okay, so that would be this one here. Yeah, question?
So the doublet would show up twice because there's a bromine in the chlorines? Or where would it, or would there be 2 doublets on that?
No, so we have essentially the doublet. Here's the doublet. Oops. We observe the doublet from these 2 protons here. Okay, there's 2 protons. They have 1 proton in red on the adjacent carbon. So there's 2 protons that are split into a doublet. And then we have this triplet, and that is a peak just for this proton here, and it's a triplet because it has 2 protons on the adjacent carbon.
Question.
Yeah.
When you're referring to these doublets, would they have greater integration because there's 2 of them, so would they be higher?
Right, so the doublet, yeah, that's what I was trying to show down here. So this number 1 to 2 refers to the integration. So the doublet, because it's worth 2 protons, would have twice the area. Yeah, you're exactly right. Okay, everybody get that? Any other questions? Okay, so the splitting.
Professor,
Yeah.
what determines the outside magnetic field?
The external magnetic field is determined by that big superconducting magnet.
I mean, like, with the last example, you designate it as pointing up. Doesn't matter.
By what's called the Pascal's triangle. Have you seen this before? Okay, so we start at the top. So for a singlet, we get one peak, right? There's no splitting. For a doublet, what we do is we just bring the 1 and the 1 down, and we split them. So for a doublet, we get 2 peaks in a 1-to-1 ratio. Okay? We bring the 1 down on the outside, and then we add these 2 1s on the middle to get 2, and we carry a 1 on the outside. So for a triplet, we get 3 peaks in a 1-to-2-to-1 ratio. All right? If we have a quartet, remember we saw a quartet before, that's when we had a CH3 next door. We carry down the 1, we add the 1 and 2 together, we get a 3. We add this 2 and 1 together and get a 3, and we get a 1. So a quartet gives us 4 peaks in a 1-to-3-to-3-to-1 ratio. Okay? And we can carry it on down. So let's see if we had a molecule like this. Now let's go back to blue. CH, and we had a CH3 here and a CH3 here. Let's think about this proton right here. Okay, first off, how many signals would you see in this spectrum? In the proton NMR spectrum. Just 2, right? Because we have essentially a plane of symmetry that goes right down through the middle here. So we have one signal for the CH that I circled in red, and both methyl groups would be together in one signal. So if we think about this red signal, how many peaks would be in that signal? How many equivalent protons are on adjacent carbons? 6, right? Both methyl groups are the same. So we have 6 protons on adjacent carbons. So how many lines would we have in that signal? 6 plus 1 is 7. So this should be what we call a septet, is 7. That's down here. So we get 7 peaks in a 1-to-6 to 15-to-20 to 15-to-6-to-1 ratio. Okay? So I probably can't draw it, but I'd have something like this. 1, 2, 3, 4, 5, 6, 7. It would look something like this. Okay? The distances between each of these peaks, if I drew it right, would all be the same and would all equal this J value is the coupling constant. Okay, but they're all split by the same amount. All right? Let's see. What do I have on the next slide? Okay, so on the next slide, maybe just from the book, and this just gives, kind of what we were working through, gives a lot of common patterns, right? So here's, okay, let's quiet down, I'm still talking. Here's what I did first, right, with two CHs. And so we see these 2 signals, and they're both doublets. And then I did this one with a CH and a CH2, and here's a triplet and a doublet. Here's one that we talked about before as well, has a CH2 next to a CH3, and so we see a quartet and a triplet, right? And so there's a couple other ones. So when we start to look at spectra, we can not only look at a single peak at a time, but if we can look at a couple together as a pattern, then that helps us a lot. Okay, so I think by tomorrow we'll be ready to start looking at some actual spectra.